Go ahead.
All right, everybody, welcome to the set theory seminar. Our speaker today is Brent Cody from the Virginia Commonwealth University, and it's always good to have you here, Brent, and I'm glad that because of these virtual seminars, we can have you here more often now that you're not at CUNY. Go right ahead.
Yeah, that's right. Thank you very much for inviting me, and thanks everybody for being here to listen. So I'm gonna talk about some work I did last year, and I've given 2 talks already on related topics, which you can sort of view as being applications of higher indescribability. So last year, I think I gave a talk in the last fall in the CUNY seminar on higher indescribability. So I'm going to do my best to not repeat myself too much. So I'm going to cover mostly some things about derived topologies, which, yeah, like I said, is some work I did last year. I also gave a talk in the Barcelona seminar on some related things, not derived topologies, but on higher indescribability and some applications to the ineffability and Ramsey hierarchies. And that is joint work with Peter Hawley, which I guess Peter is here. Okay, so I just want to start by recalling some basic definitions from topology. Everyone, I'm sure, is familiar with this already, but if you have a topological space X and a topology tau, and a subset of X, we say that little x is a limit point of this subset A. If for every open neighborhood of that point X, the neighborhood intersects the set A in some point other than X. This is the notion of limit point from basic point set topology. And then on this space, we have the Cantor's derivative operator, which is written little d. And when you apply d to a set A, it's just defined to be the set of all limit points of the set A. And we say that a point X is isolated in a topological space if the singleton of that point is open in the topology. And a space is discrete if and only if every point is isolated. So discrete spaces are sort of trivial, where the topology is just the entire power set. So I'm going to talk about some examples of topological spaces on ordinals. So the interval topology on an ordinal is defined in the usual way. So we're going to call this tau 0. And it's generated by this collection B0, which contains the empty set as well as all the intervals below delta. So we have some fixed ordinal delta. And then an ordinal alpha less than delta is not isolated in this topology, if and only if it's a limit ordinal. And if you look at the derivative operator on this space, it's just the expected thing. D0 of a set A is defined to be the set of limit points of A in this topology. And it's equal, this is equal to the set of points alpha less than delta, such that alpha is a limit and A is unbounded in alpha. So in a sense, this D0 of A is just sort of the usual set theoretic notion of set of limit points of A. And also notice that if the cofinality of alpha is greater than omega, so if alpha has uncountable cofinality, then and alpha is in D0 of A, then D0 of A is a club in alpha. Okay, so this is the interval topology. It's a sort of a standard topology on an ordinal. And now we can define a new topology called the club topology on an ordinal delta. And we will call this tau 1. And tau 1 is generated by this collection B1, where we take the intervals, that's B0, union with a bunch of derived sets. So the idea is you take the interval topology and you just declare that all the derived sets from the interval topology will now be open in this new topology. And so this extends, so tau1 extends tau0, and you can see that an alpha less than delta is non-isolated in this topology, if and only if its cofinality is uncountable. And for A contained in delta, we have the Cantor derivative on the space D1. All right, so by definition, D1 of A is the set of limit points of A in this topology. And it turns out this set D1 of A is equal to essentially the set of stationary reflection points, or the set of points in which A is stationary. Okay, so that's all straightforward. Yeah, this is known as the club topology. Okay, and you could keep going with this. The tau2 topology is obtained similarly. I should say, I didn't mention this before, but when I say generated by, and when a topology is generated by a collection, we mean this collection is a sub-basis for the topology. So tau1 is the set of all unions of finite intersections of things from B1. So tau2 is defined similarly. We just take the old sub-basis B1, and now we declare that all the derived sets from the previous topology are now going to be open in tau2. This produces a larger topology. And now if you dissect the definitions, you can see that for alpha less than delta to be non-isolated in this space with tau2, we must have that whenever alpha is in D1 of A, there's some beta in D1 of A intersect alpha. So this is just the definition of what it means for alpha to be non-isolated, right? So any neighborhood of alpha must contain some point other than alpha. So in other words, and because these D1 of A's are now open neighborhoods in the tau2 topology, in order for alpha to be non-isolated, we need to know that whenever alpha is in D1 of A, there's some beta in D1 of A intersect alpha. So in other words, another way of saying the same thing is that stationary reflection has to hold at alpha. Okay, so for alpha to be non-isolated, we have to have stationary reflection at alpha. And in fact, it's not too hard to see that not only do we need stationary reflection, but we also need pairwise simultaneous stationary reflection. And this is a consequence of the fact that B2 is a sub-basis for this topology. So, not only are these sets D1 of A open, but also the finite intersections of these sets are open. So if we go through these final 3 bullet points on the slide, if you suppose you have 2 stationary sets in alpha, A and B, but they have no common stationary reflection point, so there's no beta less than alpha in which both A and B are stationary. Then when you intersect these 2 sets, D1 of A and D1 of B, then you just get the singleton alpha. And so alpha is isolated. And so in order for alpha to be non-isolated, we need pairwise stationary reflection at alpha. And Bagharia proved that there's actually an equivalence between these 2 things. So an ordinal alpha is not isolated in the tau2 topology on delta if and only if pairwise stationary reflection holds at alpha. And 2 says that B2, this collection, which is by definition a sub-basis for tau2, B2 is actually a basis for tau2 on delta, if and only if below delta stationary reflection and pairwise stationary reflection are equivalent. And so the natural question that Bagharia addresses is, what about tau3, tau4, etc.? So these topologies are formed by, starting with the interval topology and declaring more and more derived sets to be open. And you can just continue this process transfinitely. Okay, so what happens there? So if we have an ordinal delta, we define this sequence, which is the sequence of derived topologies, tau0, tau1 through tau c, as follows. So if we're given some tau c, then dc denotes the Cantor derivative on the space delta with that topology tau c. So dc of A is just defined to be the set of limit points of A in that topology. And we define tau c plus 1 to be the topology generated by the previous subbasis together with the derived sets from the previous space. And at limits, we use unions. So if C is a limit ordinal, tau C is the topology generated by the union of the previous subbases. So this defines a sequence of topologies on an ordinal delta. And one thing Bagaria does is looks for a principle somewhat like pairwise stationary reflection that will work to characterize the non-isolated points of these spaces. And so this is the definition that, or this is a preliminary to a definition that will work. So this is a definition of C stationarity, which is an iterated form of stationary reflection. You can think about it that way. So for a subset of delta, A is called zero stationary in some ordinal alpha less than delta, if and only if it is unbounded in alpha. And A is C stationary in alpha if for all zeta less than C, whenever B is zeta stationary in alpha, there's some beta in A intersect alpha such that B is zeta stationary in beta. So this is almost like an indescribability hypothesis, if you're familiar with indescribability, because we're saying that A is C stationary in alpha means that for any zeta less than C, whenever B is zeta stationary in alpha, that reflects to some point in A. The fact that B is zeta stationary in alpha reflects to some point in A, right? Below alpha. And if you look at this definition, and you take C to equal 1, it's easy to see that one stationarity is equivalent to just the usual notion of stationarity. And another thing I wanted to point out here is that no ordinal alpha can be alpha plus 1 stationary under this definition, because if alpha is the least such ordinal, then the definition implies that there's some beta below alpha, which is alpha stationary, but beta plus 1 is less than alpha, so that beta would also have to be beta plus 1 stationary. So no ordinal alpha can be alpha plus 1 stationary. Okay, and now there's another form of this sort of iterated stationary reflection, but this is a form of iterated pairwise stationary reflection. This is called, this S stands for simultaneous. So for A subset of delta and alpha less than delta, A is 0 S stationary in alpha if and only if it's unbounded in alpha. So that's the same as for the previous definition. But now A is CS stationary or C simultaneously stationary in alpha. If for all zeta less than C, whenever you have a pair of sets in alpha that are zeta S stationary, that reflects to some point in A for both of the sets. So whenever you have a pair of subsets of alpha that are both zeta S stationary, there's some beta in A such that both S and T are zeta S stationary. That's a typo. This should be zeta S stationary there. So this definition, yes,
Brent?
yes.
I mean, are we supposed to read the definition as automatically having that xi is less than sup A delta?
Say that again. Psi is less than sup A.
Xi, is this automatically less than delta sup A? I'm just asking how we read the definition.
I
mean, you're defining this.
I think that this is defined for all ordinals psi.
And it's going to stop.
But it is trivial for psi bigger than delta, or at least delta.
Okay.
Yeah, so you can take, yeah. And I'm going to talk about that in a second.
Okay, thanks.
Yeah. So this notion, as far as I know, this notion was independently isolated by Bagaria as well as Brickhill and Welch. And I believe that was in Hazel Brickhill's dissertation. Yeah, and yeah, so Philip can confirm that, but he's shaking his head, so I guess that sounds right.
No, I'm nodding actually.
Oh, you're nodding. Yeah. Oh, you're nodding. Yes. He's shaking his head up and down. Right. So notice, right. So one S stationarity is equivalent to stationarity. Alpha is 2S stationary if and only if pairwise simultaneous stationary reflection holds at alpha. And then, yeah, I wanted to make these points also that a precursor to this definition was considered in a paper by Bagharia, Magador, and Sakai. But this was only for Xi less than omega, so for finite Xi. Yes, and Brickel and Welch there's an unpublished paper in which they study an equivalent notion, and also they studied the same thing in Brickhill's dissertation. But for the most part, I'm going to focus on the applications to derived topologies, and there will be one more result here, I think, that is attributable to Brickel and Welch. Okay, right. So this notion of iterated simultaneous stationary reflection can be used to characterize the non-isolated points in these derived topologies. That's what this theorem is saying. So for every ordinal Xi, an ordinal alpha less than delta is not isolated in the Xi derived topology on delta, if and only if alpha is Xi S stationary. I guess I forgot to say that when we say that an ordinal alpha is Xi S stationary, it means, you know, it's Xi S stationary as a subset of itself. Okay. Right, so this tells us that you know, the Xi derived topology is not trivial, or it's not discrete on delta if and only if some alpha less than delta is Xi S stationary. Okay. So we have this characterization of the non-isolated points in these derived topologies, and you know, a natural question is, you know, can it actually be that these topologies have non-isolated points? So how do we know it's consistent that non-isolated points exist? And you can use large cardinals to show that non-isolated points exist. So a certain indescribability hypothesis about alpha implies alpha is Xi S stationary, and therefore you have non-isolated points in these spaces. Okay. So let's talk about a little bit about pi1 Xi indescribability. So what are pi1 Xi formulas? What do they look like? Well, we have the classical notion of pi1n and sigma1n formulas, right? Pi1n formulas are simply formulas that involve second order quantifiers, and you have, like in a pi1n formula, you have n alternating quantifiers beginning with a for all quantifier. And then this phi here is essentially a first order statement in which you allow second order variables, of course. But there's a natural sort of generalization of these types of formulas to pi1 Xi and sigma1 Xi formulas, where Xi is infinite ordinals, can be an infinite ordinal. So a pi1 Xi statement where Xi is a limit is a conjunction of length Xi of formulas phi sub zeta, where each phi sub zeta is pi1 zeta. And similarly, sigma1 Xi formulas are disjunctions of phi sub zetas for zeta less than Xi, where each phi is sigma1 zeta. And then at successors, you just define pi1 Xi plus 1 formulas in the natural way. You essentially take a pi1 Xi plus 1 formula is essentially a sigma1 Xi formula with a universal quantifier at the beginning. Okay, and so Bagharia gave this definition of pi1 Xi indescribability. A subset A of kappa is pi1 Xi indescribable if every pi1 xi sentence that is true about v kappa reflects to some point in the set A. So there's some alpha in A such that v alpha satisfies the same formula.
Brent, can I ask a quick question?
Sure.
For these pi1c, sigma1c formulae, is there some sort of normal form theorem? So any sort of infinitary formula can be put to be one of these forms?
I don't know. I don't know about that actually. Yeah, that's a good question.
Okay, I guess I'm just trying to figure out exactly what this expresses, but maybe that's not a great question. Thank you.
No, that's a good question. I'll show, we will talk about some expressibility results, and hopefully that will motivate these definitions a little bit more.
Okay, awesome. Thank you.
Yeah, it turns out that like this way of defining it is quite natural within this context. Hopefully that'll be clear.
Can I also ask a related question?
Sure.
So when you take these infinitary conjunctions and disjunctions, should I worry whether I suddenly have infinitely many free variables that I need to quantify away? Do I care?
That's a good question. By definition, these formulas only involve finitely many free variables, second order free variables. Yeah.
Okay. Thanks.
That's a good question. I mean, I'm being a little bit hand wavy here with the definition, but yeah.
Sure. Okay, thanks.
Mm-hmm. And right, and I also wanted to mention that the Brickhill and Welch paper, or yeah, the Hazel Brickhill's dissertation. Actually, Philip, do you guys use indescribability in your paper with Brickhill? I don't think so.
Yes.
Oh, you do. Okay.
Yes.
Also, there's an older paper by Ian Sharp and yourself, right? Ian Sharp and Philip Welch.
Yes.
That involves transfinite indescribability, right?
It does.
That definition is different. That definition is
Yeah.
in terms of games, right?
Yeah, it's a game theoretic definition, and it's an open question as to whether those two versions are exactly the same or not.
Okay, I'm glad you said
I'm
that.
hoping
Because
somebody will answer this question.
yeah, I'm glad you said that, because people have told me that they are equivalent, but I haven't been able to verify that myself. So.
Right, I suspect they are, but that's all I'm going to say. Right.
Yeah. Okay.
Right. Could I perhaps ask? I mean, it looks like for your definition at the successor levels, I mean, we have this kind of sigma 1n plus 1 in describability is equivalent to pi 1n in describability. So that looks like, I mean, you could ask this at the transfinite level. Is this, looks like it holds here with your definition?
It does hold here, yeah.
Right. I mean, I think that's a test question for the game theoretic version, actually, as to whether this, the Sharp-Welch successor, sigma 1 psi plus 1 in describability is the same as pi 1 psi. That would be one way of showing they were different.
I see, yeah.
Failed. Okay, thank you.
Yep. Okay, yeah, so this is where you can sort of see where these classes of formulas are coming from. And so essentially you want to be able to express xi stationarity using a pi1 xi formula. And like if you look at the definition of xi stationarity or xs stationarity, this is one way you can sort of understand where this definition is coming from. So for example, yeah, this lemma says that for all xi less than delta, a subset of delta, and all cardinals alpha less than delta, you can express that A is xs stationary and alpha using a pi1 xi formula over V alpha. And this is pretty easy to see. A is 0s stationary, just means that A is unbounded in alpha, so clearly that's a pi1 0 expressible. And if you look at the definition of xs stationarity, A is xs stationary in alpha if and only if for all zeta less than xi, whenever S and T are XCS stationary in alpha, there's some beta to which that reflects, right? So for limit Xi, this definition is pi1 Xi expressible over V alpha inductively. You can take a conjunction of all overall zeta less than Xi of the pi1 zeta statements that A is zeta S stationary. And then for successors, if you just write out the definition, it's not too hard to see that the successor case is also expressible by the right type of formula.
Could I ask a quick question?
Sure.
In the lemma, alpha is a cardinal. Is that essential to the proof, or is it just you don't care about anything else because cardinals are clubbing?
Yeah, that's a good question. It certainly is the case that we don't care about anything else, but I don't know if it's essential for the proof.
Okay, I won't care about it then.
Okay, yeah, that's a good question. It might be. Yeah, that's a good question though. Okay, so then Bagaria also proved that every pi1 Xi indescribable subset of kappa is Xi plus 1 S stationary. So this is how you can get sort of from large cardinals, you can get the consistency of these iterated simultaneous stationary reflection principles, which then give you the non-discreteness of the derived topologies. And so this is just sort of a standard argument, standard reflection argument. Right, so if A is a pi1 Xi indescribable subset of kappa, and you suppose you have, and this is bad notation here, this A should be some other thing because I have an A here, these are different sets. But the idea is if you have two sets that are zeta S stationary in kappa, you can express this with pi1 zeta assertions over V kappa, and then using the indescribability, you can reflect that to some lower beta, right? And then because these things actually express the right type of stationarity, you get what you want. Okay. Right, so to sum things up, this is another result. In L, there's a correspondence between Xi plus 1 stationarity, pi1 Xi indescribability, and Xi plus 1 S stationarity, as well as non-isolated points in these derived topologies on delta. And this is where I was going to say, but part of this result is independently due to Brickhill and Welch. One of these if and only ifs here. They show that in L, kappa is pi1 gamma indescribable, if and only if kappa gamma reflects gamma stationary sets. This is their terminology. Okay, so in summary, delta is an ordinal, and we have these derived topologies on delta, the sequence of derived topologies, tau 0, tau 1, tau 2, etc. And we can use indescribability to obtain these iterated stationary reflection principles, and then those principles can be used to characterize the non-isolated points in these topological spaces. But there's a problem, which is that these results break down when you get to tau sub delta. So we have a sequence of topologies on the ordinal delta, and these results of Bagaria break down when you get to delta. And the reason is no cardinal alpha can be pi1 alpha indescribable, and no cardinal alpha can be alpha plus 1s stationary. So you can see that no alpha can be pi1 alpha indescribable by considering the statement, let's see, for all beta less than alpha, there exists an ordinal of order type beta. Okay, that is a pi1 alpha statement that is true about V alpha, but it can't reflect below alpha, right? So some infinitary sentences are, in a sense, too long to reflect below alpha. Okay, so this all means that alpha is isolated in the derived topologies whose indices are above alpha. And so the sequence of derived topologies terminates at delta. At delta, the delta derived topology is discrete is the power set of delta. And so our goal here is going to be to modify Bagaria's definitions so that these results can actually be extended beyond delta.
So is the idea going to be something like alpha can be pi1 beta indescribable for every beta less than alpha or something like that?
That is the idea for the very first step. Yeah.
Mhm,
Yeah.
mhm,
Yeah.
Okay. Could I just, I had another question. So, so when you define this sequence of topologies, you always throw in the derived sets for all subsets of the ordinal that you're talking about. Is it worthwhile, or has anybody looked at just restricting that? Not using all subsets, but say only subsets consisting of ordinals of a certain cofinality or something like that?
I don't know. Yeah, as far as I know, no one has thought about that.
Mm-hmm.
Yeah,
I see.
And I'm not sure how to answer that right now. That's a good question, though.
All right.
Okay, so right. So the key idea in doing this is these various diagonal notions of the things involved. So we're gonna use diagonal notions of indescribability, iterated stationarity, and diagonal Cantor derivatives. So so we have an ordinal delta. We have this sequence of topologies, tau c on delta. And so let's just define a function d sub delta. This is not, this is not going to be the derivative operator with respect to a given topology. We're just defining this function by saying that d sub delta of a is the set of alpha less than delta such that alpha is a limit point of a in the tau alpha topology. So in order to determine whether or not alpha lives inside of this set, we are using the alpha-th topology, right? So which topology we are using here in the definition is dependent on alpha. And then we'll see that we can redefine the delta-th derived topology to be the topology whose closed sets are the C's which are closed under this function. Okay, so we're sort of somehow viewing the derivative operator as being the thing that leads to the delta derived topology. Okay, and it's not too hard to see that at least for the first step here, for delta, things work out. So you can show pretty easily that if alpha is pi1 zeta indescribable for all zeta less than alpha, then alpha is alpha S stationary. And furthermore, the non-isolated points in this topology defined in this way are precisely the alphas which are alpha S stationary. Okay, so at least for this basic case, things sort of work the way you want. Okay, so right, so you can define topologies from derivatives. So if you're given a function d and a set x, and this function d is from the power set of x to the power set of x, and you want to use this function to define a topology, you can do this, right? This is a standard thing. But you need the function d to satisfy certain properties if you want things to work out. So if d satisfies these properties that we will talk about, then the collection of all u contained in x whose complements are closed under this function is a topology on x. So this tau sub d is just the topology whose closed sets are closed under the function d. So the properties we need this d to satisfy are 1, 2, and 3 here. No, property 1 just says that the derived set of the empty set is going to be the empty set. Property 2 says for any sets a and b, subsets of x, if a is contained in b, then d of a is subset of d of b. All right, so this is, you can think of this as saying if a is contained in b, then any limit point of a is going to be a limit point of b. Similar statement for unions. Also for all x in x, if x is in d of a, that has to imply that x is in d of a minus singleton x. Okay, so like if you write down this definition of tau d and you try to verify that this is actually a topology, it turns out the things you need are exactly property 1 and property 2. Okay. Now, beyond that, if you want this topology to have its derivative operator equal to the function you started with, then you need this third property. So for all a contained in X, d of A is contained in d of A union A. Okay, and it's not difficult to check that the diagonal Cantor derivative that I mentioned earlier satisfies these three properties. Okay. So now the question is, okay, this sort of does what we want, but only for one step, right? So we have the sequence of derived topologies on delta up to delta, and now we have a derived topology on delta that behaves the way we want it to. And so now we want to move beyond delta and continue the sequence of derived topologies above delta. And so to do this, we're going to use canonical functions. So what are canonical functions? So now let's suppose delta is not just an ordinal, but a regular cardinal. Then this sequence, which we'll notate with f sup delta sub xi for xi less than delta plus, this is the sequence of canonical functions at delta, and it has a bunch of properties which I'll mention, and I'll tell you sort of the important parts for what we're going to do in a bit. But for each index xi, these functions are functions from delta to delta. For zeta less than xi, we have that f delta zeta is less than f delta xi modulo the non-stationary ideal. So this just means that the zeta function is less than the xth function on a club. So this sequence of functions is increasing, right, in a sense. And if J is any generic ultrapower by a normal measure or a normal ideal on delta, then the xth canonical function represents xi in the generic ultrapower. Okay, and sort of more important for us is this slightly more concrete way of looking at canonical functions. We can take these functions to be defined as follows. So for xi less than delta, the xth canonical function is just the constant function xi. And then for xi between delta and delta plus, we are going to assume that we have a fixed bijection from delta to xi, and then that the xth canonical function is defined by taking that bijection. So if we want to say what the xth canonical function is equal to when you plug in alpha to it, you take the bijection from delta to xi, you take the pointwise image of alpha, and then you collapse it, or you take the order type of that image. And we're going to assume that the deltath bijection is just the identity function. Okay, and you can think of these canonical functions as sort of allowing you to take statements about delta that involve xi and reflect them to alphas below delta. And when you do that, the xi sort of becomes f delta xi of alpha. So you can think of f delta xi of alpha as being alpha's version of xi in a sense. Another related sequence of functions, which I call in my paper the sequence of canonical reflection functions at delta, is essentially the same as the sequence of canonical functions, but the values of these functions are non-transitive. So the only difference between these functions and the canonical functions is right here, we do not put the collapse there. We don't put the order type there. That's the only difference. And so these functions are from delta to p delta delta plus. They're still increasing in a sense. And in generic ultrapowers, they don't represent ordinals, but they represent, like the xth canonical reflection function represents J image xi. Right, and we're gonna assume that we are using this sort of more concrete form of these functions. Let's see, do I miss anything else here? Oh yeah, just notice that they're related, of course, in this way, that if you take the xth reflection function at alpha and you compute its order type, it just gives you the same as the Cth canonical function. And we're going to assume we're using the same sequence of bijections to define these functions. Okay, so how can we define higher derived topologies for Xi above delta? So we're going to define some functions, Bxi, Txi, and Dxi. And we also define a topology, tau Xi, on delta, inductively, according to this. So what we do is for Xi less than delta is we just use the same definitions as Bagharia. Tau Xi and Dxi are exactly the same. And then for these functions, we're going to define Bxi to simply be the constant function. For Xi less than delta, this makes sense because we have Bxi as defined by Bagharia. And then also tau or Txi is going to be constantly equal to tau Xi. Okay, and so the interesting stuff happens when we look at Xi values between delta and delta plus. And if you look at this definition for Xi equal to delta, it is the one that we already discussed, the sort of more basic diagonal Cantor derivative that we already discussed. So what do we do? So for Xi between delta and delta plus, Bxi and Txi are functions with domain delta. And what is Bxi of alpha? This is going to be the sub-basis for the Xith topology, which is used to compute whether or not alpha is in Dxi of A. Okay, so if you go back to the definition of diagonal Cantor derivative that we already looked at, this is sort of a natural generalization of that. So we're using these bijections in order to determine which derived sets are going to be placed into these subbases. Okay. And then Txi of alpha is just the topology generated by that Bxi of alpha. Okay, so and then once these two definitions have been made, Bxi of alpha and Txi of alpha, we can define a map Dxi. And again, this is not a derivative operator yet, but we just define the map in this way. And then we let tau Xi be the topology whose closed sets are closed under this map Dxi. Okay, so hopefully that makes sense. So if you take Xi to equal delta, then this B sub delta delta is the identity function. And so the zetas that we're using are just the zetas that are in alpha, right? Then that gives us a sub-basis for Txi of alpha. And so then D sub delta is just the alpha is less than delta, where alpha is the limit point of A in the tau delta topology. Okay. So one thing you have to worry about is like, does this definition really work to produce a topology? And does it have the properties that you want? And so there's a lemma here that says essentially that things work the way they should. So for all Xi less than delta plus and all A contained in delta, Dxi of A is contained in Dxi of A. So this is like that third property that we had here, right? In order for the function that we started with to be the derivative operator of the topology we're defining, we need that third property. Okay, and this lemma is saying we have that third property. And you can think of this lemma as being a generalization of the fact that if a set A has stationarily many of its initial segments being stationary in alpha, then the set itself is stationary. Right. So if you unravel what these definitions are saying, it's essentially just this, but for Xi stationarity. All right, so then it's also fairly easy to show that these functions Dxi that we're defining satisfy the properties 1 and 2 that we discussed earlier. So they satisfy all 3 properties that are needed. And so these functions Dxi are the Cantor derivatives of these spaces that we're defining. Okay. And it's pretty easy to see that this sequence that we've defined of topologies on delta, and we've defined tau xi for all xi less than delta plus, agrees with Bagaria's sequence, right? So if you look at indices below delta, you just get the same topologies that Bagaria had. And what we want to do is try to characterize the non-isolated points of these spaces using some diagonal version of xi-s stationarity. Okay, so this is the definition of xi stationary that we looked at. And we already observed that no ordinal alpha can be alpha plus 1 stationary. And so what we need to do in our updated definition is sort of overcome that in some way, right? And so what you want to say is that a set A contained in delta is alpha plus 1 stationary in alpha, if and only if it's alpha stationary in alpha. And whenever S contained in alpha is alpha stationary in alpha, that reflects to some beta. But you can't expect that the alpha stationarity reflects to some beta, but you can expect that this sort of truncated version of stationarity, alpha stationarity, reflects to beta. So A is alpha plus 1 stationary in alpha if it's alpha stationary, and whenever S contained in alpha is alpha stationary in alpha, there's some beta in A such that S intersect beta is beta stationary in beta. So this is the part that is being sort of truncated, right? In Bagaria's original definition, this would have been an alpha. Okay, but now we're cutting it down to a beta. Okay, and if you do that for larger values of xi, you will use canonical functions, and this is the definition. So in general, for any xi less than alpha plus, A is xi stationary in alpha if and only for every zeta less than xi, whenever S is zeta stationary in alpha, there's a beta in A to which this reflects. In other words, there's a beta in A such that S intersect beta is F alpha zeta of beta stationary in beta. Okay, so we're just using canonical functions to push the definition of stationarity a little bit. And so you can do this similar thing with pairwise stationarity. So this is a generalization of xi-s stationarity using canonical functions. And again, it agrees with Bagaria's definitions for xi less than alpha. There's this hat S stationarity definition. This was a sort of a convenience for to simplify some of the proofs. So I might just skip a discussion of this, but notice that really the only difference between this S hat stationarity and S stationarity is that the zetas that we're picking here are coming from these non-transitive sets. Whereas over here, in the S stationary definition, the zetas are simply less than xi. It's less than alpha plus. Okay, but to simplify some of the proofs, I worked with this definition. It turns out that this definition is just equivalent to this one on a club, so it doesn't matter really which one you use. But yeah, this is saying that for any xi less than delta plus, there's a club on which these two definitions coincide. So yeah. Okay, so if delta is regular, xi is less than delta plus, there's a club c xi and delta such that for any A contained in delta, dxc of A intersect that club is equal to the set of alphas in which A is xi s stationary in alpha. So this is sort of building up to characterizing the non-isolated points in the tau xi topologies. Yeah, and so if you look at what this is saying, when xi is equal to delta, we just have that alpha, for any alpha less than delta, alpha is a limit point of A in the delta topology, if and only if A is alpha s stationary in alpha. Okay, so these theorems are essentially saying that this works. You can push these things beyond delta and things work out. But a common feature here when you do this kind of thing is that it doesn't work for all alpha, but it works for club many alpha. So if delta is regular and c is less than delta plus, and for all alpha in C sub C, where this C sub C is the club from the previous proposition, for all alpha in this club, the ordinal alpha is not isolated in the tau C topology on delta if and only if it is C S hat reflecting. Okay. And this corollary is just rephrasing things in terms of the non-hat reflecting properties. Okay, so then, you can characterize the non-isolated points in these higher order derived topologies using these diagonal stationary reflection principles. And then the next thing we want to do is use indescribability to show that such iterated stationary reflection principles are actually consistent relative to large cardinals. And this is where higher indescribability comes in. Let's see. We talked about expressing zeta as stationarity over kappa, so I think I'll skip this for now in the interest of time. And I spoke about this higher indescribability stuff in the seminar last fall, so you may or may not remember, but the idea is that what do these higher indescribability principles say? So when you look at pi1 Xi formulas, which are where Xi is less than kappa plus, say, these are formulas which have length longer than kappa. So you can't in general expect that you can reflect such formulas, but what we can do is reflect fragments of such formulas. So we say that a set A contained in kappa is pi1 Xi indescribable, where Xi is less than kappa plus, if for every pi1 Xi sentence over V kappa, which is true about V kappa, there's some alpha in that set, this should be an A, such that a restriction of the original formula is true about V alpha. So phi itself doesn't reflect to alpha, but a restriction of phi reflects to alpha. And this definition agrees with Bagaria's for Xi less than kappa. And this restriction I've defined here. Yeah, so, right, so the idea is if you take a formula phi, which is pi1 Xi, and Xi happens to be less than kappa, then when you restrict the formula, nothing changes, essentially. You're just cutting down the parameters. But for the interesting values of Xi, like where the formulas are very long, when you restrict a formula of length Xi, you get a new formula which is shorter, which has length given by a canonical function, right, at alpha. And this is an inductive definition, of course, because we're also restricting the component formulas. Right. Yeah, so I gave a talk last year about this stuff, but the point here is that you can express Xi stationarity using pi1 Xi formulas, even for Xi values which are above the cardinal that you're looking at. So if kappa is regular and Xi is less than kappa plus, then there's a pi1 Xi formula that expresses Xi S stationarity of a subset of kappa over V kappa in such a way that the restrictions of that formula also express the F kappa Xi of alpha stationarity over V alpha. And that's for club many alpha. Okay. Okay, so if a cardinal kappa is pi1 Xi indescribable for some Xi less than kappa plus, then it's Xi plus 1 S stationary. And moreover, if you have enough highly indescribable cardinals below some regular cardinal mu, then there is an alpha less than mu, which is not isolated in this higher derived topology. So this is for any c less than mu plus, right? Okay. So there are a lot of natural open questions around this sort of thing. The results of Bagaria that I mentioned at the beginning were continued. There's another paper by Bagaria, Magador, and Mancia. And there are also some additional results in Bagaria's paper that I haven't yet generalized to these higher derived topologies and higher stationarity and so on. So there are a lot of natural questions about whether or not that can be done. I expect the answer to these would be yes. And then you can also ask, essentially given any sort of classical result about stationarity, you can sort of ask the same question about these Xi stationarity. And, for example, can the ideals associated to Xi stationarity and Xs stationarity be saturated? This may be related to like saturation questions for like the ideals associated to indescribability. Helston proved that like the pi11 ideal can be saturated relative to a measurable cardinal, and so similar techniques might be usable in this type of situation as well. Okay, I will stop there.
Okay, thanks a lot.
Thanks very much,
talk.
Brent.
Sure.
Are there any further questions?
Yes, I can put up a hand. Yeah.
Yes, Philip, go ahead.
Okay, I think well, no, that was very beautiful. I'm glad to see these things being extended. I suppose one question is, well, we've already discussed it about whether, I mean, for me, it's interesting as to whether the notion in the paper with Ian Sharp, the notion of the indescribability is equivalent to this indescribability property that you have, or generalizing Joanne's definition. Certainly, I think the game theoretic version gives you a kind of, somebody asked about whether there was a universal pi1 psi formula or whatnot. So I think you can get a universal formula out, at least from the game theoretic definition.
Yeah, and I show that these exist also in this context in my paper.
Oh, you do? Oh, right.
Yeah.
Okay.
But
so,
yeah, I'd be interested to see that for the game version too.
Right. I suppose my main question, or at least one of the things that Hazel was looking at, was in particular was downwards absoluteness questions about whether something, if you've got a cardinal, if it's 2 stationary, n stationary, is it 2 or n stationary in L? Right. So the results there were, you had to make some extra assumptions about the normality of what would be the n club filter or the psi club filter. So I mean, I think the motivation in the definitions in her thesis came more from generalizing the idea of clubness rather than generalizing the idea of stationariness. So this was sort of a slight change of perspective, right? So, although of course, in the end, the definitions of stationarity and so on come out to be equivalent, right? I mean, once you build in, we built in this notion of being simultaneously stationary reflection into the definition of a cardinal being reflecting. So there's kind of slight modifications there. But do you know about any kind of downwards absoluteness results? I mean, from 5 stationary sets, 5 stationary cardinals, are they 5 stationary in L?
Yeah, that's a good question. I would have to look at Joanne's papers to see if he has anything in there.
I don't recall anything from.
Yeah, I don't either, but yeah.
I mean, I think we could get something like 2 stationary sets reflecting, but anything more than that required extra assumptions about the normality of these filters.
I see, yeah.
And maybe the same thing would happen here, I conjecture, but I don't know. Maybe someone has a smart way of avoiding that.
Yeah, that's a good question. Another thing I could say is that I mean, maybe it's obvious, but I think you guys defined like the gamma club sets, right? And I think the sets which are playing the role of those here are the derived sets, right?
Right.
And I suspect that, you know, I'm not sure about the exact indexing, but like if you look at a set of the form D sub gamma of A, this will be a gamma club in your definition, right?
Yes, I think
Something like
that sounds,
yeah.
That sounds right. Yeah, right. Yeah, so in our preprint, we took over Joanne and other people's definition of this D sub psi and
Right.
showed just that. I think showed just what you said.
Oh, I see. Okay. But yeah, I think the question about like whether these two notions of indescribability are equivalent is interesting.
Yeah, that should be answered.
Yeah.
I mean,
that was like one of the first things I thought about, but I didn't make much progress. So
right.
Yeah. There seems like there's probably some sort of quite complicated coding that would be necessary.
Right.
I didn't have a question before, but something Philip said now gives me a question because of the situation with normality. So I was just going along assuming, there's going to be some ideals, there's going to be normal ideals, everything is going to be similar to what I'm accustomed to with lower levels of indescribability. Apparently that's not the case. So what is the situation? Are there, in particular, suppose we end up getting some not normal ideals this way, and then we try to make them normal, just close them up under diagonal unions. Do we get anything interesting that way? Is it obviously a silly thing to do? What's the story on that?
Yeah, that's really interesting. So all of the indescribability ideals are normal, but the ones that are sort of in question are the Xi stationary ideals. And like if you assume a cardinal kappa satisfies enough indescribability, then the Xi stationary ideal is normal. But I don't know much beyond that. Yeah, I don't know if Philip could say anything else about it, but
no, I think I could. No, I mean, you've said as much as.
I think it's an open question about like if kappa is not pi1 Xi indescribable, can the Xi stationary ideal be normal? I think that's an open question. You might look at the paper by Bagaria, Magador, and Mencia to see something there. I'm not completely familiar with that paper, so there might be something in there.
Okay, thank you.
I also realized I have a question now after Philip's earlier question. So, downward absoluteness is all well and good. Do you have forcing technology for, taking a whatever stationary set and, shooting whatever you need to shoot to decrease the level of stationarity of a given set?
Yeah, that is in the Bagaria, Magador, Mencia paper. Yes.
And it works even for these extensions above above
For the higher
your
for the
diagonal
diagonal
versions.
notions. Yeah, well, that I'm not sure about. I don't think anyone has looked at that yet, but I would expect that they would.
All right.
Yeah. But yeah, I mean, I think there's a lot of room for asking additional questions about those forcings, like in any sort of classical thing you can do with club shooting forcing. You could say, can we do that with C club shooting forcing, right?
Okay, great. I think, are there any more questions? I don't want to cut off an interesting discussion. So seems like everybody is happy. Okay.
I'll just mention some references here. I mentioned the paper by me and Peter's here. Hi, Peter. There's this paper that we posted on the archive recently. This blue paper is where most of the material I talked about today is coming from, and these are the other sources that I mentioned.
Interesting. Okay. All right. Thanks a lot again. It was a very interesting talk.
You're welcome. Yeah.
Well, Brent.
Thank you. Great.